Thank you very much, Professor Sakaguchi. I want to thank first the Tohoku Forum for Creativity to organize this nice program. I was really hampered by the officers that work at this project. Everything was perfect, and really thank you for helping me in everything, my needs. And also want to say that this is my fifth time that I come to Sendai. The first one, I visited Sendai to organize the first Italian-Japanese workshop. I visited Professor Ishige, and then the next year there was the first workshop in Sendai. Ever since we had so far 5 workshops, Italian-Japanese workshops. And from that visit, it started a collaboration between the University of Florence and the University, the Tohoku University. Actually, we have, our university supports with little money the exchange between the two universities. So if somebody wants to visit Florence, we can support local expenses, either local expenses or the flight. So now I will start with my talk. And so this is the title. These are famous mathematicians, and why are they connected? Are they connected? The first connection is between Alexandrov reflection principle and Serrin's overdetermined problem. So Alexandrov reflection principle was created by Alexandrov to prove the famous soap bubble theorem. That is a C2 smooth compact hypersurface immersed in Rn with constant mean curvature is a sphere. The idea of the proof is quite simple. The surface is a sphere if and only if is mirror symmetric with respect to planes for any direction, orthogonal to planes. So if you can prove that, you prove that it's a sphere. To prove that, Alexandrov created the reflection principle. I will, this is, say, the historical part of my talk. So I will just give a brief overview of the proof of Alexandrov and Serrin, but the focus of my talk will be on the proof by quadrature identities and the connected stability results. So, the observation that Alexandrov does is that you take a plane and you start reflecting the surface with respect to this plane until the reflected portion doesn't get out of the domain surrounded by the surface. It's better to look at the picture. What happens? Can happen something like that. You reflect and you stop until you touch a point on the other side of the surface. Or it can happen something like this. You reflect and stop until the reflected surface is tangent at some point here, P. So S prime is the reflected surface. And so in those two situations, you can locally represent the two surfaces by the graphs of two functions defined on a ball. In the first case, defined on the ball. Okay. Yeah, on this little ball locally. So U prime is this, U is that one. Or half a ball on this plane here. So you can see this portion of the surface of the surfaces as the graph of functions defined on this plane here, the vertical plane. Sorry. But at this point, you observe that locally, the two surfaces are solutions of a differential equation. The differential equation for non-parametric constant mean curvature surfaces. And this is an elliptic equation. And by using the strong comparison principle, you get a contradiction in the first case. The two surfaces are solutions. If they touch, they must be equal. And in the second case, you use Hopf boundary lemma that gives you a contradiction. This is all what I will say about this. For Serrin, Serrin refined the proof of Alexandrov to apply to this overdetermined boundary value problem that entails the torsional rigidity. The torsional rigidity is defined as a solution of this equation with boundary value 0. And the overdetermination which is given is that the normal is constant on the boundary. Then Serrin proves that the domain must be evolved and the solution must be quadratic. That is, the graph should be a paraboloid. Which are the differences now between the Alexandrov reflections principle and Serrin's method of moving planes? Sometimes they are called by the same name, method of moving planes, but they are a little bit different. Because in Serrin's proof, there is something else, something new. The good news is the hypersurface now, which must be seen in Rn plus 1, is already a graph of a function on the domain omega. The bad news is that S has a non-empty boundary, while before we had a compact surface. Another news, so the expected symmetric surface is a paraboloid and not a sphere. So what Serrin does is he takes planes which are orthogonal to horizontal directions. Okay, but it's better to see this yeah. So horizontal directions, and then the other problem is that the border of the surface is in common with the boundary of omega, and that means that we are on the boundary of omega, and the strong comparison principle is ruled out. Nevertheless, Serrin refines the proof and gives a proof by contradiction. Let me see, let me go to the pictures, which are better to see. I did the picture in the plane Rn, in the space Rn, omega is the subset where the function u is defined. So this is the intersection of a vertical plane, that is a plane orthogonal to horizontal directions. And so the first critical position is obtained like this. At some point, you reflect this, and you touch at some point on the boundary. Then you consider the solution. The u prime is the reflected solution. U is the original solution. You consider the two functions here, and you know that they are equal here, and they are one less the other one here on this part of the boundary, and they're equal here. And so you use by the strong maximum principle. In the case of the torsion problem, is the maximum principle, but in general would be a strong comparison principle. You get that u prime is less than u, and more importantly, at the point P, since you have a touching ball here, because you are supposing that the boundary is C2, you get that the normal derivatives should be different. But since P is a point in common, at the same value, it's a minimum point, you get a contradiction. That is, it's a point in which u prime and u equal, and u is larger than u prime. There, you should have a contradiction. What is new? So you use the Hopf maxim of lemma here, but what is new in Serrin's proof is that the second occurrence is this. You reflect, and you have a point P here, and the plane cannot be pushed further. Otherwise, you get out of the domain. And here, you cannot apply the Hopf maximum principle because you have a corner. In the domain here, you have a corner, so you cannot fit a ball, a touching ball. And I don't get in details, but Serrin solved this problem by what is called now Serrin's corner lemma. That entails, besides the first derivatives on the boundary, also the second derivatives in directions that that stem from the point P inside the reflected domain. And so this is what is called Serrin's moving plate method. Okay, now, I'm sorry. Okay, now let's look at the other connection between the other two names of the title. And so the proofs by integral identities and inequalities. So Weinberger gave a different proof of Serrin result by using integral identities and inequalities. And Reilly instead gave a proof of the subbubble theorem based also on integral identities and inequalities. So you see, started with subbubble theorem, then Serrin result, Weinberger new proof of Serrin result, and then Reilly gave a proof of Soap-Bubble theorem. So the circle is closed. Okay. So the important observation that Weinberger and Reilly use is that if U is the solution of the torsion problem, that is Laplacian of U equal n and U equals 0 on the boundary, if you show that this quantity is identically equal to 0, you show that omega must be evolved. Why? So this is a spherical symmetry test. It's a spherical symmetry test because this quantity is always larger than or equal to 0. For instance, by the Cauchy-Schwarz identity, the inequality, because you take the scalar product of the Hessian matrix with the identity matrix. You use Cauchy-Schwarz and you get this inequality. This is the way to see it. And the Cauchy-Schwarz inequality holds with equality if and only if the Hessian metric is the identity matrix. So what you get here, you get that U must be a quadratic polynomial that you can arrange in this way with the center and a radius there. But you know that U, since now is a quadratic polynomial, you know that U is equal to 0 on the boundary. And so the boundary, you get on the boundary, you get the equation of a sphere with center x bar, and the radius, you can compute it by some divergence theorem. Since U is constant equal to R on the boundary, you can compute the constant, which is important in my talk. So the ratio between the volume and the area of gamma times n. And in the case of Reilly, Reilly's proof, if H naught is the constant curvature, then H0 must be the reciprocal of that number. Anyway, I will just give a review of this. Then later I will show you that we can encode the two proofs on two identities, not inequalities, but two identities. And the two identities give more information about what we were looking for, the stability of the symmetric configuration. So in both cases, Weinberger and Reilly, they use what is called the P function. This is the P function, whose Laplacian is the quantity that we use to test symmetry. I recall that U, it will be always the torsion function, the solution of the torsion problem. So Weinberger then uses the maximum principle. P, by that inequality, is subharmonic, so has a maximum. The maximum is on the boundary. On the boundary, the U is equal to 0. The gradient of U is equal to R. And so you have that P is less than this constant. But then you take this integral, and by the Reilly-Pohozaev identity, you prove that this integral is 0, but is the integral of a positive function. And so that function must be identically constant. But if it is identically constant, then its Laplacian must be 0. And so you obtain the symmetry test. The Reilly-Pohozai identity is an application of the divergent theorem to some differential identity. So, why does okay, no, it was. So in the case of Reilly's proof, Reilly's idea is to regard the surface, the compact surface, as the boundary of the domain omega, in which we have the solution of the torsion problem. And then to use this formula, the Laplacian of U can be written this way, where H is the curvature of level surface of U, and nu is the normal to the level surface, which is the gradient of U divided by its modulus. You see this, since gamma is the level surface of U, you can consider this on the boundary. And then what you can do, you proceed, you multiply by U nu, both sides, and you integrate on gamma, and you use two formulas. I'm sorry, but I'm using. Okay, so you use you multiply and integrate this identity. And you use the divergence theorem and the Minkowski identity. This is the Minkowski identity. The integral of the curvature times the scalar product of the x minus z vector field is equal to the area of gamma. But since you know that h is constant, the constant pass out of the integral, and this integral gives you n times the volume of omega. So you get h0, and by this identity and the use of the divergence theorem, you get that the integral of the Laplacian of p is equal to 0. But since you know the Laplacian of p is always larger than 0, so the Laplacian of p must be identically 0, and so you get symmetry. Now, let me make a pause here and explain about some motivations and some ramifications of these problems. One is concern the Saint-Venant's principle, that tells you that if tau is the torsion of a bar of cross-section omega, of an infinite bar with cross-section of omega, then among all sets having given volume, the ball maximizes the torsion. So this is a classical result. So the torsion is defined this way, and it turns out that tau of omega can be computed either by taking the integral of the square of the gradient of the torsion function, or by this. The two integrals are connected by the divergence theorem. I recall you that my u is negative. Okay. So one proof of this result was given by Polya and Zeglo in the book, in their book, can be found in their book, and is based on rearrangement techniques. Here I want to show a connection with the Serrin's overdetermined problem. And the connection is this. Once you prove that a domain omega 0 exists that maximizes the torsion among the domains with given volume, then you can use what's called domain differentiation. The domain differentiation, that is the domain omega naught is embedded in a family of domains, in a one-parameter family of domains, and you take the derivative with respect to this one parameter, and then you should have some critical point. And is what one can do. So this is the one parameter family. So the idea is to take this function of t, which is the what you get if you do the technique of Lagrange multipliers. So if omega 0 is a point in which the maximum is attained, this function should have first derivative equal to 0 for some Lagrange multiplier. One way to construct the family is to let the domain omega t be the image of the base domain omega 0 by a family of mappings, which are the identity for t equals 0, and have the first derivative at 0 given by some normal, the normal to the boundary of omega 0, times some compactly supported function. So this way you are perturbing the domain in the normal direction with some intensity which is modulated by the function phi. If you take the derivative, so you denote by ut the solution of the torsion problem relative to the domain omega t, and you consider the quantity that I showed you before, if you take the derivative and evaluate at t equals 0, after some manipulations, you get this integral. So if you require that the derivative is equal to 0, you have that this integral must be equal to 0 for any choice of the compactly supported function phi. And since phi is arbitrary, then you get that the normal derivative, the square of the normal derivative must be constant. And then you can put that constant. The constant lambda must be r squared. And that is U satisfies Serrin's overdetermined problem. So this is the first connection. The second connection is to what was considered by Payne and Schaeffer in a paper of 89, which they noticed that a solution of the overdetermined problem by Serrin exists if and only if these two quantities equal for any harmonic function inside omega. So if you notice, this is the mean value of u on the domain omega, and this is the mean value of of h on the domain omega, and this is the mean value of h on the boundary of omega. And it's easy to prove that it's just a consequence of Gauss-Green formula, n times h, n is Laplacian of u, Laplacian of h is 0 because h is harmonic, then you use Gauss-Green formula and you get what you want, and vice versa. So that one, as I said before, is a kind of mean value property for the domain omega. That is, the mean value on the domain is equal to the mean value on the boundary of the domain. A domain like that has been named a harmonic domain. So Serrin results says that the Euclidean ball is the only bounded harmonic domain in Rn. Should be noticed that the paper by Payne and Schaeffer, the title is Duality Problems. So they stress the fact that the formulation they give is a dual formulation. And why? Because it entails a linear functional. That is, if you take the difference between the two mean values, and so this gives a linear functional from the set of continuous function of the boundary to R, to the real numbers. And here, what you do, you have H on the boundary, and you extend as a harmonic function inside the domain. You can even compute the norm of this function, and you get this quantity. So it's evident now the connection. If nu is the constant R, you get that the functional is 0. And so the norm of the functional is 0, and so you get equality between the two mean values. One more connection is to the theory of quadrature domains that was initiated by Aronov, Gustafsson, and Shapiro. I forgot to put the name of Shapiro. So a quadrature domain is a domain that was considered by the three authors in R2 because in their mind they were holomorphic functions, is a domain that satisfies what is called the quadrature identity. That is, for every holomorphic function in the domain, the integral of the holomorphic function is a finite sum of constants, complex constants, and derivatives of the holomorphic function evaluated at some point in omega. For instance, if you take m equal 1, n1 equals 0, p1 equal p, and the constant equal to the volume of omega, you get the mean value property. So you have a special quadrature domain. A domain satisfying the mean value property for holomorphic function is a special quadrature domain. Why quadrature? Because this is the quadrature formula. So the integral can be computed by a finite combination of values of the function. That's why it's called quadrature domain. This notion can be extended. Instead of the finite sum, we can put the integral with respect to some measure, signed measure, and also can be extended to Rn by replacing holomorphic function by harmonic functions. And so a by this terminology, a harmonic domain is a quadratic domain if we choose the measure d mu as a multiple of the surface measure of gamma, on gamma. So now let's get to the core of the talk. That is a slightly newer proof of symmetry in the case of Reilly, of subbubble theorem, and Serrin's problem, by using some integral identities. The first integral identities that we gave with Poggesi, a student of mine, we realized that if we don't use inequalities, we don't throw anything away, we can write an identity satisfied by the solution of the torsion problem. And so we get the integral of this quantity that we learned. It's important. This is also is important. It connects to Serrin's overdetermined problem. On the right-hand side, we can put the curvature. If we take H naught as the number that I showed before, the exact number that I showed before. The next identity is useful for Serrin's problem. The difference here is that we put minus u in front of the quantity, and we get this identity. And so here you get this difference, that if it is 0, we get 0 from here. And to prove this, it's important that R is that quantity there, H naught is that quantity there, and so those numbers, they come from the divergence theorem. In one case, if you use R, then you use the divergence theorem and you compute R, while in the case of the subbubble theorem, H naught can be computed by using the Minkowski identity. So the Minkowski identity is, according to me, is the counterpart of the Reilly-Pohozzai identity in the case of the torsion problem, because it entails this vector field here. So let's do some comment on this the first identity. This is the identity. It is clear that since this is the sum of two positive numbers, it's enough to know that this integral is less than or equal to 0 to get symmetry. Because if this is less than or equal to 0, then both summands here will be 0. And so we get a little bit more than Alexandrov subbubble theorem. For instance, it is enough, since this is positive, it's enough that this term here is less than or equal to 0. So if the curvature is larger than H naught, you get symmetry. So it's enough to know that H is larger than H0 to get that this is 0, but also that this is 0. So h equal h naught or larger than h naught gives both symmetry or overdetermination in Serrin result. And this term here will be used to get better stability identities. So, as I said, if this is larger than or equal than h0, you get also that the normal derivative is equal to r on the boundary. In the second identity, if this integral is less than or equal to 0, since the integral on the left-hand side is positive, minus u is positive by the strong maximum principle, and this quantity is non-negative by Cauchy-Schwarz inequality, then if the integral at the right-hand side is less than or equal to 0, you get symmetry again. But if you notice, you can get symmetry if u nu is equal to r, or if u nu minus this quantity is equal to 0. But this is really trivial. If you get this, you easily show that, u is a quadratic function. But still, this information will be used in the stability estimate. And another comment about this formula that the proofs can be extended to less regular domains. The formula is perfectly valid if gamma is C1 alpha instead of C2. But it can be even weakened, the assumption on the boundary. Oh, just one comment about Serrin principle. We noticed that we recall the derivative of that functional is that integral, and if you choose phi equal to that and lambda equal to r squared, then really the identity becomes like this. The integral on the left-hand side is equal to the integral of the derivative of the function, of the parameter. So this confirms and extends the Serrin principle, and it's enough that you take derivatives only in particular directions. So, of course, if omega naught is the maximum of the torsion, you get 0, but it's enough to choose particular directions. Other identities can be written, for instance, by rearranging the identity for Bubble theorem. We can write this, and this tells you, since u nu is positive on the boundary by the Hopf lemma, that if 1 minus h u nu is equal to 0, or u nu is 1 over h, this is another overdetermined boundary value problem, and you get symmetry in that case. One more identity that can be obtained and rearranged. This identity has been derived by Antonio Ross, not the identity in inequality, but you can write under the form of an identity, and so you have the sum of two positive terms and this quantity. And so that means that that quantity is larger than or equal to 0. So you get this inequality, which is called the Heinze-Karcher inequality. And so if the quantity is 0 here, you get, again, symmetry. So now it's time for stability. So I have, yeah, I think I'm on time. So the idea is to use the two identities to get stability estimates. What does it mean, a stability estimate for radial symmetry, for spherical symmetry? That is, so roughly speaking, what we want to measure quantitatively how far a domain can be from a ball if the deviation of h from a constant, of u from a constant, is measured in some norm. Okay. One way to do this is to find two balls, one inside omega, one outside omega, with the same center, and estimating the difference between the two radii by a function of eta, where eta is some norm of the deviation of h from h naught, or of a deviation of u nu from the number r in some suitable norm. So is what one way is this. It's a kind of uniform estimate. So this is the situation. The situation. There are the two spheres that enclose the domain omega, the surface gamma. It's clear that rho I, the radius of the inner ball, is the minimum of x minus z when x is on the boundary, and rho I is the maximum. So the whole problem is to find z, a proper z, and a proper psi. So the results that we have with the Poggesi in two papers, the second paper improves the first paper, is this, that we can choose as a norm the L2 norm. This is the stability result for Soap-Bubble theorem. So we can enclose gamma in the difference of the two balls of radius rho I and rho E. And the difference can be bounded by a constant times the L2 norm on gamma of the difference between the constant H0 and the mean curvature of the boundary. This is for n equal 2 and n equal 3. For n larger than 4, we have this exponent, and we cannot get more better than that so far. Here we get the optimal exponent, and so the constant depends on various parameters that can be reduced to the dimension, the volume of omega, the diameter of omega. Of course, we can discard the volume, the diameter would be enough. And these two numbers, Ri and Re, which are the radius of the largest ball in omega that touches omega, the points of the boundary. And this is the largest ball of the complement of omega that touches the boundary. So that's it's a bound on the principal curvatures of the boundary. So this estimates These estimates improve some estimates given by Chirao and Maggi, in which they used a uniform measure of the deviation. We use L2 deviation, and they were giving them for strictly being convex surfaces because they use the Heinz-Ekash inequality based on the proof of Antonio Ross. And then we improve the exponent. They have this exponent in general, and we have a larger exponent. And in the case n equal 2 and 3, we get the best exponent that you can expect. Even if you consider a weaker measure of the deviation. Other estimates that one can get is using some modification of what's called the Frankel asymmetry. This is a measure of asymmetry. You measure the deviation of the volume of omega from the volume of a ball. You take the inf among all the balls with fixed radius r, and in our case you get an estimate with the best possible exponent. But it should be noticed that from that you don't get from that inequality there, you don't get a better inequality in the estimate with the two balls, the inner and the largest and the exterior ball. Yeah, because you get that this difference can be estimated by the Frankel asymmetry to the power 1 over n, and that gives a poorer estimate. For Serrin's problem, we get this. The deviation is in L2 norm, and we get the exponent 2 divided by n plus 2. And this is for all n larger than 2. There is not, there are not the two cases that we have for the soap bubble theorem. And this improves on previous results. The first ever was given by Astalion, Busca, and Reichel, and they got a logarithmic estimate using a C1 norm of the deviation, but they get it for a more general problem. So a semi-linear equation, and the reason why they get a logarithmic estimate is because they use Harmonic inequality. They use the Serrin's method of moving planes. Since in the symmetry case, one uses the strong maximum principle, so the quantitative version of the strong maximum principle is Harmonic inequality. So they use Harmonic inequality, and so Harmonic inequality, you get the constant that goes exponentially, and so if you take the inverse of this exponential function, more or less you get a logarithm. Then there is the proof of the estimate by Brandolini, Salani, and Trombetti that used the torsion function. So it works with f equal n, a constant, only in that case, like in our case, and they get an estimate of polynomial nature. Then with Ciraulo and Vespri, I got an estimate in the spirit of Aftagon-Buscain-Reicher's estimate, and also works for semilinear equations, in which we get a polynomial stability by modifying the measure of deviation. This is the Lipschitz seminorm of the function u. And then recently, there is a paper by Felsen that proves an estimate that considers the asymmetry, the Frankel-like asymmetry, and there is a polynomial estimate, but we improve with our exponent. So now let's look at the proof. The proof is based on some easy remarks. First of all, the function h obtained by the polynomial, the quadratic polynomial q, a generic quadratic polynomial q, minus the torsion function u. That's a harmonic function, because both the Laplacian of q and the Laplacian of u are equal n. So it's a harmonic function. And on the boundary, h is equal to q because u is equal to 0. So this is the first remark. A second remark is that the quantity, the important quantity that the symmetry test, for which we have the symmetry test, is really the Hessian, the norm of the Hessian of the function h. Then other observation is that h is equal to q on the boundary, and so the difference between the square of the radii of the two balls, of the two possible balls, is the oscillation of h on the boundary. And also you can estimate this difference by some constant that depends on the volume, because Re, the bigger ball, contains omega, and so you can estimate its volume by the volume of omega. So the whole problem is reduced to finding a connection between the oscillation of h and this quantity here. So the two identities that I wrote before can be written this way. The integral of the L2 norm of the second derivatives of h can be put in here, and this here there was u nu minus x minus z dot mu that can be written as h nu, the normal derivative of h. So now with these specifications, now the proof runs into can be divided into 3 steps. For instance, in the case of the curvature, the mean curvature, by the identity that I showed before, the first step is easy. You bound the normal derivative of u by a constant m. That constant m can be controlled by the diameter and the number r sub e. And so you bound by m squared times the deviation of h from h naught in L1 norm. The second step is to estimate the L2 norm of a harmonic function by the L2 norm of its second derivatives. But this cannot be done if you don't choose the point z property. The third, we will see then the second step, how it works. And the third step is proving that the oscillation of H can be bounded by the L2 norm of H raised to some power. So this is the most difficult step in which we lose something. So if you put together these three steps, you get this inequality. Notice that this is not the inequality that we get in the theorem, because there should be a 2 here and a 2 here. But this is an intermediate inequality. So the second step can be attained by taking the infimum of the L2 norm of the derivatives of a harmonic function with the constraint that the L2 norm of the function is equal to 1, V harmonic, and V of x naught equal to 0. So that normalization is important to get that this if is a minimum, and so this number is positive. And in our case, this number can be used by choosing z. So we choose z in such a way that h of z is equal to 0, and the gradient of z is equal to 0. And so what we obtain is that the L2 norm of h can be estimated by the L2 norm of the derivatives, but then also each derivative is 0 at the same point. So I apply this estimate here, and I teach first derivative, and so I get this inequality. So to make sure, we have to choose z in such a way that h of z is equal to 0 and the gradient of h is equal to 0 at that point. And we can choose a critical point of view. U is negative and doesn't have a critical point on the boundary. So, for instance, the minimum of U is a critical point of view. But if we choose that critical point to be the center of the polynomial Q, also the polynomial Q will have a gradient 0 there. And so we get that the gradient of H is equal to 0. The second normalization, we choose the parameter A that we had in our polynomial. So that we proved in the first paper that this minimum exists. Then we realized while writing the second paper that it can be derived by a more general Poincare type inequality proved by Zimmer in 86. So now let's get to the third step. So it works like that. So we take a point on the boundary, x, and we go inside following the normal. And we get to the point y at a distance sigma. And then we define the domain omega sigma as the domain that has distance of the points that they have distance from the boundary larger than sigma, the parallel set. So the first thing we do, h of x, we want to estimate h of x. So h, by choosing x as the maximum point of h on the boundary and the minimum point on the boundary. So we get an estimate of the oscillation. We use the fundamental theorem of calculus in the direction getting inside. So we can estimate by the value of y and the integral of a derivative in that direction. But then we roughly bound the gradient by its maximum. And the maximum of the gradient of h can be estimated by the maximum of the gradient of u that we already considered, and the maximum of the gradient of q that can be estimated by the diameter. So we get this first inequality. Now y is a point inside the domain. And since it is inside, we can use the mean value property, since h is a harmonic function. So the value of h at y can be estimated by using the mean value property. So we take a ball, a maximum ball that touches at the boundary, center y, hy can be written as the mean value on that ball that can be bounded by the integral of the absolute value of h. Then we use Hölder's formula, and we get this quantity here, and the L2 norm of h on the ball that can be estimated by the L2 norm on the whole domain. And so we get some inequality that depends on sigma. We put together this, and so we get this inequality. And then we minimize with respect to sigma, as long as sigma stays in the interval 0 Ri. And we get that h of x is bounded by the L2 norm to that power, and that's the reason why we have this point. But in order to make sure that sigma is between 0 and Ri, we must choose the norm. The norm should be sufficiently small. Then, final step, we estimate the oscillation by the sum of the absolute values of the values of h at the point in which the maximum is reached and a minimum is reached. And so we get the first step. In the case n equal 2 and n equal 3, there is the Sobolev embedding. So you can estimate the semi-norm of a function v in W22 by the Hölder norm. I mean the semi-norm, in the Hölder semi-norm by the L2, the W22 norm of v for some constant c, some embedded constant c, and gamma is any number between 0 and 1 for n equal 2 and 1/2 for n equal 3. And so this gives So we have an estimate that entails the Sobolev norm, but the Sobolev norm is the norm of the function, or the L2 norm of the function, plus the L2 norm of the first derivatives. So with the inequality of the second step, we can always obtain an inequality, that inequality with an exponent 1/2. And hence we get this inequality that has 1/2 here, but not 1, but here we have 1. Oh, here must say that a slight improvement of the inequality can be obtained by putting, instead of the L2 norm, you put the integral of the positive part of h0 minus h. So the constants depend at this point, as you see, they depend on some geometrical parameters and some spectral parameters, mu0 and the Sobolev embedding constant. But this can be estimated with some results in the literature, depending only on the geometric parameters. Another improvement is that since the point Z can be chosen as any critical point of the function U, then we can have also an estimate with an aggregate of balls. So if a domain like this may have 2 maximum points and also a saddle point here, and so we can get an approximation in which inside we take 2 balls, and outside we take the intersection of the big balls. And the radii of the balls can be estimated in a quantitative way. For Serrin's problem, the proof of the stability runs more or less in the same way. The only difficulty is that instead of having 1 here, we have a minus u. That goes to 0 when x goes to the boundary. But here, so we get this intermediate estimate with the L2 norm, L1 norm, but here we noticed that minus u can be estimated from below by the square of the distance for every point in omega, or by just the distance times I if I'm sufficiently close to the boundary. This is just a comparison that you do with the solution on the solution of the torsion problem with the solution of the torsion problem in a ball touching the boundary. And here we use this weighted Poincaré type inequality, and that was given by Boas and Straub in 1998, and generalizes the result of Zimmer that I showed you before. But it should be noticed that the difficulty that we have with the function u at the boundary doesn't influence the exponent, but just the constant, the stability constant. So again, the oscillation can be bounded by, so this is step 3, that runs unchanged, then you get this inequality and the presence of the factor u doesn't influence the exponent. So now, how to improve the exponent and get the exponent that we have in the theorem? We didn't use this fact. We didn't use when the normal derivative tends to a constant. Also, h nu tends to 0. So, we will use this fact to double the exponent. And but we must do this in a quantitative way. So we must estimate h nu in some norm with some norm of u nu minus r. And I'm sorry. And this can be done by an inequality that was proved by Feldman. So you can bound the L2 norm of h nu by the L2 norm of u nu minus r. That's why we have the L2 norm, and not the L1 norm anymore. And so we can conclude that the difference of the two radii, which can be bounded by this quantity, can be bounded by using Hölder. So we bound u nu plus r by some constant, and then u nu minus r times h nu. We use Hölder, and so we get we bound by a constant c double prime times u nu minus r to the power 2 to the n minus 2. And so we get we can double the exponent, as we said in the theorem. In the case of Alexandrov soap-bubble theorem, we must rearrange the identity in order to get h nu somewhere. And so we have the deviation of h from h naught, the deviation from h naught. This goes to 0, as we saw in the identity for soap-bubble theorem, because when the right-hand side goes to 0, there the left-hand side goes to 0, but in the left-hand side we have the L2 norm of the deviation of u nu from r. And so we rearrange the things in this way, and use again and get from the identity, we discard this, which is positive. We get that the L2 norm squared of u nu minus r can be bounded by a constant times the deviation of h from h naught times u nu minus r, because here we use Hölder, and here we use Feldman inequality. So we get this inequality, so we can simplify for this quantity and get that the deviation of u nu from r in L2 is controlled by the deviation of h naught from h. So it's not stable. It's not stable. And so we get the final estimate. This one is unchanged. It has the exponent tau n, And in the end, we get this exponent. Tau n divided by 2, and here tau n. Tau n is our exponent. For n equal 2 and 3 is 1. For n equal 4 and more is the 2 divided by n plus 2. Some, if I have time, I want to show some byproducts. So you get also stability estimate connected to the Symmetry principle. So you can control by this derivative, you can control the spherical symmetry of the domain when you have chosen as function phi, a specific function. And then a stability for harmonic domains. The way to measure the deviation is by controlling the norm of the functional. So here, the norm of the functional in L2 will be the norm of u nu minus r in L2 times some constant. So this is, use this. And so it's a stability for harmonic domains. And then other byproducts are stability estimates for the Heinze-Kachel inequality. And yeah, or for the other overdetermined boundary value problem. These are the essential references, and so thank you very much for your